information that remember before examine, I explained you like effect of the compressible, no compressible of the air atmosphere, because atmosphere is gas, right? Main difference between gas and liquidos is that it's gas is compressible, liquid is not compressible. But it's in general. But in practica, gas like atmosphere acts sometimes as a non-compressible, and in some condition it's compressible. And it depends of velocidad, like avion moving in air in atmosphere with subsonic velocity, with subsonic, when it's Mach number less than 1. Air that moves around all sides of the avion is acting as a non-compressible. It's just moving around solid. It doesn't increase or decrease density. And that's why air acts as a non-compressible in subsonic flow. If avion increases velocity, increase velocity, and it comes to sonic, after that on subsonic velocity, what happened? This solid like avion pile up, it's kind of collecting in front of itself like air, that it's like slowly increasing density. And when avion reaches sonic velocity and goes to the supersonic, air that moves around avion, it acts as a compressible. It's changing density. That's why like in those general conditions, when it's atmospheric compressible and atmospheric non-compressible, Bernoulli's principle works in this situation poquito different. In both the situations, Bernoulli's principle absolutely works, but how it does it's a little bit different. Example, when we speak about subsonic, first changes velocidad, and as a result, it's changing pressure. For example, on the top of the airfoil, velocidad increases, pressure decreases, and as a result, it's creating lift for the subsonic. For the supersonic flow, when air is compressible and changing density, increasing density or decreasing density of the air, what happened? First changes pressure. Like pressure increases, and as a result, velocity drops down. Or pressure decreases, velocity goes up. But in both the situation, like Bernoulli's principle works, but a little bit opposite way. So that's why form of the avion, form of the airfoil, supposed to be different for the subsonic and supersonic flow, because of in subsonic flow, this is airfoil. Can you see this slide? Can you see picture, people?
Yes, teacher.
Yes, teacher.
So in sub, I'm just repeating a little bit just to refresh for you, like from previous class, because this is important. So this part, like this part, it's airfoil, and this is traditional, like positive asymmetrical subsonic airfoil. And what happened here? Subsonic wing and subsonic flow. Flow, it shows this way. It's just like in general, it's not exactly like that, but it's like it shows character, like how it happened in general. And we can see nice movement of the air around airfoil, and in some condition, if it's not too high velocity of the airfoil, there is no any separation point just behind here, very Chiquita separation point just behind stagnation point, and it doesn't create so huge magnitude of the arastra, but it's still creating lift. And here what happened, like increasing velocity, and as a result on the top, like decreasing pressure, and as a result it's creating like lift force, upward force. This is subsonic wing in subsonic flow. Now imagine this wing, subsonic wing, it goes from the subsonic, it goes to the sonic and supersonic. Excuse me. What happened here? Very first, in supersonic flow, very first, just in front of the this airflow, in some like huge part of the front of the airflow, it's creating, it's inducing air to increase density. It's compressing air in front, and it stays like stick to the airflow. And this part is very high density of the air. It just in front, and it just pile up this air, and it's here Mach 1, porque it just sticks to the surface of the airfoil, and this part high density, and it's creating very strong resistance. And behind this part, we have like supersonic flow, because it's when it goes to supersonic flow weighs Mach number more than 1, and it's creating a lot of separation points because of forma of the airfoil, and creating a lot of turbulence here. So, and it's in general, it's very negative for the subsonic airfoil to fly to in supersonic velocity. Next, if we see supersonic wing, it's like a rhomb forma. It's flat, this kind of forma. It's not traditional, this airfoil forma, subsonic. This is supersonic forma. And what happened when it's moving with subsonic velocity? With subsonic velocity, all around this airfoil, a lot of separation of the air. And porque air now acting, it doesn't change density, it's acting as a non-compressible. It just separates from every edge of this airfoil, and it's a lot of separation and a lot of arastre. And it's creating just a little bit lift. But when this airfoil, supersonic airfoil, goes to the supersonic flow, it just works perfect. Porque there is no separation points, and everywhere Mach number is more than 1, and it's very efficient flight with minimum arastre. So we can say subsonic wind in subsonic flow is very good. Supersonic wind in supersonic flow is very good. Subsonic wind in supersonic flow, problema. And supersonic wind in subsonic flow, also problema. This is general information about form of the wing and velocity of the avion. And when it's subsonic flow, it's not compressible air. It's here and here. And with supersonic flow, it's compressible air, and it's not good for the subsonic airfoil. And the supersonic airflow is not good in subsonic flow. So here a little bit about another problem about aerodynamics heating. When avion goes, not just avion, let's say any flying object like avion, it could be a rocket, it could be missile, any like flying object, in moving object in air. When it goes to the Mach number more than 1, it's stagnation point increasing magnitude of the arrastre, stagnation points. Stagnation points in airfoil, it's very front part of the airfoil and very rear part of the airfoil. And in stagnation point, velocity equals 0, so pressure is atmospheric. And that's why at stagnation point, it's always creating like arrastre, huge arrastre. Plus, when avion, when this solid like airflow goes to the supersonic speed, temperature increases. Temperature, it appears because of friction of the surface of the solid with air. Air has density, and this density creating very strong friction. Example, like this is for every simple like avion, and it's difficult to understand, maybe to believe first time that it's air can make surface of the moving transport like to melt and to get rojo, to get in plasma condition, like increasing velocity, faster velocity, greater temperature. And so sometimes it's creating around this moving object like just plasma, and it's very difficult, almost not possible for any magnetic, radio, electromagnetic signals to go through this plasma. It's working as a shield. It doesn't let any like signal go through this shield. That's why if you have like some moving object like no pilot, like controlling from distance, to send information to control trajectory, for example, this information maybe cannot go through this plasma. And that's why this kind of devices, it's very difficult to control, to change trajectory, to change some another parameters of the flight. And this is because of aerodynamic heating. Aerodynamic heating is very important problem, and this problem appears with increasing velocity when it goes from supersonic to hypersonic. Especially high hypersonic velocity, it's aerodynamic heating became critically important. Questions so far? This is information was from, I guess it was from previous class, and now questions so far? No?
No, teacher.
No.
Now a little bit math about wing platform. ¿Por qué? Porque so far we spoke about like cross section, right? Cross section of the wing, like airfoils. And airfoil, now you understand that we have like subsonic airfoil and supersonic airfoil. And here about platform. Platform, it's just like we have in general, just this is just really in general, 1, 2, 3, 4 types of the wing platform that if we see from the top or from the below of the avion, it has like this formas. And this formas, just wait, I have to, because I cannot see. So very first, it's rectangular wing, straight rectangular forma. Elliptical wing, from the word ellipse, elliptical wing. It's third one, it's taper wing or moderate taper wing. It has like some kind of trapezia forma, this kind, and swept back wing. And this wing, or sometimes we call it delta wing or flying wing, the same. It's a form of the wing of the avion for the sonic and supersonic flights. So very quick like analysis, like general analysis of each of them. Like rectangular wing. This forma is good for the slow flight. Slow flight. It's low velocity. Most likely it has like a internal combustion piston engine and propeller. And so velocity, it's around like 300, 400 kilometers per hour maximum. And very efficient this wing. And stall effect or like a lot of resistance occurs first on the root. This part is root, it's a raíz. It's the raíz of the wings, and it's from the raíz but mostly it's concentrated near the like wing and fuselage in this area. Next one, oops. Next one, elliptical wing. Elliptical wing, it's more efficient. ¿Por qué? Porque this ellipse forma, it's smooth, nice forma. It doesn't have sharp edges. That's why it's most efficient because of less arrastra, creating less arrastra. But here another problema. It's compared to first one, it's much more like a production process, much more difficult production process of this forma. This rectangular, it's compared to this one, it's simple. This one much complicated. It means that it's more expensive, and stalls concentrate all along trail edge. Stalls with separation point. Separation point concentrates everywhere like along trailing edge. Next one, next forma is the moderate tapered wing, and it's trapezia forma wing. For example, this kind of forma, we have kind of this forma, like actually this forma and this mixed, we have in our Cessna 182 in our laboratory. So this, it's more efficient than rectangular than this one, and easier to build manufacturing process than elliptical. But still, it's like during the flight, it's concentrated like arrastra and separation point along all this trailing edge of the wing. See this area. Next one, swept back or like delta or flying wing type of the avion, and this one is just good for the supersonic and supersonic velocity, but not really good in subsonic. But remember, this avion cannot fly from the zero velocity right away to the supersonic, right? It's supposed to like go first to the subsonic and after to supersonic. So part of the flight this avion does in subsonic speed. When it's taking off and increasing velocity first, and second stage of the flight when it goes to the landing, it also from the supersonic it's supposed to go slow down to subsonic, and in both stage of the flight in subsonic condition it experiences like not problem, but it's not efficient. Not efficient. ¿Por qué? Porque to create lift, it's supposed to increase velocidad. With very high velocity landing process, it's kind of poquito different. Well, poquito difficult. Not difficult, not right word. Not difficult, it's specific. That's why this kind of the avions, they have like on the landing, it's also they have high velocidad. That's why they necessitate some additional devices to stop this avion. For example, parachutes. Parachutes, it helps to reduce velocity on the landing. Why? Because landing, it does like high velocidad. Just wait, people. Okay, I'm back. So this is 4 general types of the wings for the avion, and it's just general, like because of see, as I told you, like second one and third one, it's maybe we have like combination of these 2 types, like in our Cessna, it's combination second one and third one. First one is just on very like slow avions, because here like less velocity, large surface of the wing creating a lot of arrastre. It doesn't let you to create very high velocity. But if you use propeller, and you can use like very efficient like internal combustion piston engine, and you can easily fly to short distance with very high efficiency, this kind of the avions. Next, what I want to tell you today, it's some parameters of the wing, and this is aspect ratio. So in general, aspect ratio is the ratio of the wing span. Span is maximum distance from one punto of the wing to the punto of the another side of the wing. Like both wings, okay? Like in the middle here, fuselage here. So distance from here to here divided to the average chord, this is span. So see, span is aspect ratio, it's span, this distance between punto to punto to the average chord. If we have a rectangular wing, it's easy, everywhere chord is the same. So when 24, for example, divided by 6, and we can get aspect ratio 4. And here, for example, we have like elliptical forma. In this forma, span, distance from punto to punto, divided by average chord. average course here we're supposed to calculate, or somewhere in manual of the avion it shows like some the most important parameters, and it also it shows like average chord. And here aspect ratio is equal around 9. So this is aspect ratio that it's parameter of the avion that gives us an idea. Like, for example, high aspect ratio, it means that it's like more distance, more span compared to average chord. And higher aspect ratio, it means that it's like it's increasing lift force, but it's decreasing like stalling force, stalling speed, and this is a decreasing velocity when it's large aspect ratio. But it's necessity for the flying devices, for example, for the gliders or for the spy plane, spy avion that it's flying on the high altura and flying very, very slow. And you can take all these pictures what is going on Tierra. So this is about aspect ratio. Any questions?
For the moment, no, teacher.
So this is information that I supposed to present you today. It's aspect ratio, and refresh a little bit about forms of the wing and the forms for the, it depends of the velocity and depends on the compressible or no compressible. Now you know like coefficient of the lift, coefficient of the drag. Now you know about center of pressure and aerodynamic center. Now you know about like formula of the wing for the subsonic and for the supersonic. And we are going to make some laboratory this Friday. I am going to just wait for invitation, okay? If I invite you, just we are going to have class. So, and you are going to make, after this laboratory, you are going to make some calculations and some reports. After that, I'm going to go a little bit about like movement of the avion in 3D space, and what part of the avion controlling which movement. And this necessity for you to understand altogether aerodynamica, form of the avion, and parts of the avion, controlling avion in different condition and at different velocity, like for the subsonic and supersonic, for example. And that's it for today. Any questions?
I don't think so, teacher.
No, teacher, thank you.
Well, okay. So please, people, Friday, I promise you, so far I am positive that we are going to have laboratory class. But I don't know for sure if it's going to be possible or no, because it's again about this coronavirus situation. It's now it's people telling me that it's most like it's going to go to Rojo again, and it's maybe going to be closed some like restaurants, cafe, something like that. So if you want to go to table dancing, do it today, tomorrow, okay?
Okay, teacher.
Okay. No, it's maybe next week everything is going to be closed again. I don't know. And but I wish laboratory, we are going to make this laboratory activities this Friday. So far, it's positive, but again, I'm not sure 100%. Once again, if you have any questions, you can contact me anytime. I help you with any questions. And thank you for attending this class. И see you maybe Friday, or if not Friday, so see you lunes. Take care of yourself. Stay at home.
All right, teacher. Thank you.
Thank you. Bye.
Teacher, see you next class.
Bye.
До свидания, профессор. Спасибо за все.
До свидания, Имане.
Bye, teacher. Great week and great day.
Thank you, Israel. Thank you.
Bye-bye.
Bye.